For a long time, individuals have imagined what life may resemble in different universes. Because of the James Webb Space Telescope, the most amazing telescope in existence, that question can finally be examined. While observing the closest star system to us, Proxima Centauri, which is only 4 light-years away, specialists have seen a couple of specific abnormalities from one of the planets in the system, Proxima B. These irregularities, called artificial lights, have dumbfounded the best personalities in standard science. But what are they? Do these lights suggest the presence of intelligent life on the planet? Join us as we investigate the James Webb Space Telescope's disturbing discovery of city lights that could change everything. The only life that we are currently aware of is on Earth. Since the beginning of civilization, people have wondered whether there is life elsewhere in the universe. To do such an interstellar search, American cosmologists Jill Tarter and Thomas Pearson launched the Search for Extraterrestrial Intelligence (SETI) project in 1984. The project's charitable goal was to assemble space-borne radio transmissions. Radio waves can travel farther and are subsequently more likely to be detected by the 42 radio telescopes that make up the unprecedented Allen Telescope Array in the California Sierra Nevada mountains. However, in the past 30 years, no decisive extraterrestrial transmission has been found. Following that, the James Webb Space Telescope's successful launch reinforced a mission to review a range of concealed planets surrounding far-off stars. As the largest telescope on the planet, floating around 1 million miles from Earth and equipped with incredibly sensitive detectors, it has the potential to uncover groundbreaking discoveries. A while back, there were no known planets outside our solar system. However, since then, more than 4,000 exoplanets have been found orbiting various stars. According to NASA, the universe might contain trillions of exoplanets. The early signs of something happening beyond our solar system may be found in extraterrestrial vegetation. The Galileo spacecraft, on its course to Jupiter, turned its instruments back toward Earth and found a clear indication of the presence of plants, recognized in the vegetation red edge, a biosignature, a mix of red and infrared lights reflected by plants. For instance, a planet like Earth covered in a jungle should have a strong and easily recognizable biosignature. The JWST will measure the biosignature of distant, Earth-like planets in the habitable zone around stars, which could give significant clues about what might be happening in their exoplanet atmospheres. When sunlight passes through a planet's star, the JWST could potentially detect it as it enters the planet's atmosphere. The missing frequencies would then be found through spectroscopy as molecules and atoms in the atmosphere absorb specific frequencies, creating a characteristic fingerprint that the JWST can recognize. This technique may be used to determine the composition of the atmosphere and whether life is possible. Life could exist on Earth-sized planets with atmospheres like our own, made up of a combination of oxygen, nitrogen, and carbon dioxide. By looking for elements that aren't normally present, scientists could potentially detect intelligent life. For example, chlorofluorocarbons (CFCs), produced for use in refrigeration and cleaning products, would likely be detectable by observers from afar. If the JWST detects CFCs in planetary atmospheres, it would suggest the presence of civilization. However, life on exoplanets may not resemble life on Earth in any capacity. Sometimes even normal living organisms, like extremophiles, species that can survive in conditions where other living things would perish, could appear alien. These organisms, primarily microorganisms, can withstand extreme conditions, such as heat up to 250 degrees Fahrenheit or strong acid with pH levels under 3. Since planets like Earth are more likely to support life than those with extreme temperatures or acidic conditions, it may be wise to focus on those first. Prime candidates could have temperatures that allow liquid water to exist on their surfaces and orbit a stable star. Our Sun is a yellow G-type star. These stars are relatively rare and generally have shorter lifespans. However, in our universe, the likelihood of studying planets orbiting red dwarf stars, which are more common and have lower luminosities and temperatures than the Sun, is higher. This longer time span allows the development of life and evolution to produce complex organisms. About 40 light years from Earth, the TRAPPIST-1 planetary system will be the subject of the JWST's first mission. It orbits a quiet red dwarf star with 7 Earth-sized rocky planets. 3 of these rocky planets, located in the so-called habitable zone, could have liquid water on their surfaces. Despite its smaller and colder mass compared to our Sun, the TRAPPIST-1 star emits light similar to that of Earth due to the close orbit of its planets. The clearest opportunity to observe city lights outside our solar system is Proxima Centauri, a red dwarf star that is. For 0.25 light years from the Sun, Proxima is many times fainter than the Sun, so a planet would have to be much closer to it than Earth is to the Sun to support life, particularly liquid water. In August 2016, astronomers discovered a planet with 1.3 Earth masses in the habitable zone, a Goldilocks zone where the light intensity is just right to melt water. Proxima B orbits Proxima Centauri, but it is possible that Proxima B is an airless, dormant planet. Given that it orbits its red dwarf star at a distance of only 4.6 million miles. This close orbit exposes it to strong solar winds that could strip away its atmosphere. However, Proxima B receives enough sunlight for temperatures and liquid water to be similar to Earth's. It is believed to be tidally locked, always showing the same side to the star, much like the Moon does relative to Earth. Proxima Centauri has about 18% of the mass of the Sun and emits far less light than one would expect for a planet so close to its star, only about 5% of the Sun's brightness. It might seem like a scorched wasteland. Liquid water could exist on Proxima B as long as the planet has an atmosphere to retain heat, since the total energy it receives from the Sun is only 65% of what Earth gets. Nevertheless, the planet is not especially hospitable to life. It is most likely tidally locked, meaning it always faces the same side toward the star, resulting in permanent day and night with extreme temperature variations. The planet also receives up to 4 times as much high-energy radiation as Earth does, including X-rays and ultraviolet light, due to its proximity to Proxima Centauri. Proxima B is also bombarded with high-energy particles during stellar flares. Unless it has a protective magnetic field like Earth's, the conditions for life may not be favorable. Still, favorable conditions could potentially make Proxima be a more attractive world. Unfortunately, models suggest that the atmosphere of tidally locked planets may be vulnerable to rapid breakdown due to the freezing out of volatile gases on the night side. Our planet's atmosphere is replenished by volcanic activity, and for planets with strong magnetic fields, this atmosphere is less likely to escape. Since we know nothing about Proxima B's volcanic activity or magnetic field strength, we can't even speculate whether the planet has an atmosphere. However, since an atmosphere suggests the presence of oceans, and both together suggest the possibility of life, we are eager to know whether Proxima B has a complex atmosphere. It could have solar panels on the day side to generate energy to light and warm the night side, which would otherwise be excessively cold and dark for habitation. The discovery of Proxima B has sparked a race to determine whether it crosses its star's face as seen from Earth. These transits would allow scientists to determine the planet's size and mass, enabling them to estimate its density and confirm its rocky composition, giving insight into the materials used to form its rocks. During a transit, starlight could pass through the planet's atmosphere. However, the chance that the orbit will align in such a way for scientists to observe a transit is only 1.5%. The star's tendency to flare complicates matters. Astronomer David Kipping of Columbia University states that the star is unstable, as stellar flares make a rocky planet absorb sunlight and re-emit it as infrared light. However, rocky planets emit a particular kind of infrared radiation from stars like Proxima Centauri. Moreover, the James Webb Space Telescope was specifically designed to detect infrared light. Proxima B's infrared signature is the key to identifying the planet's atmosphere. Also, the infrared portion of the spectrum is significantly stronger than Hubble's replacement, which could allow the JWST to detect city lights on Proxima's night side, even if they are as faint as those currently used on Earth. The JWST could detect artificial lighting as long as it is restricted to a frequency band much narrower than the star's light. Proxima B's day side might be heavily covered with solar panels reflecting starlight. As Proxima B orbits its star, it faces a constant cycle of day and night, with cool night lows following daytime highs. The temperature difference between day and night, however, depends on whether the planet is made entirely of bare rock. If it has no atmosphere, Proxima B's day and night temperatures will vary more, as the day side will emit all the energy it receives from Proxima Centauri as a blackbody. We can calculate the exact amount of blackbody radiation that should be present. The night side, on the other hand, would be like a frozen wasteland. If the temperature difference between day and night is less pronounced, we can calculate more specific temperature differences and better understand the thermal dynamics of Proxima B. If the planet does have an atmosphere, it could act like a blanket, trapping heat on the night side and reducing temperature extremes. This could make the environment more stable and potentially more hospitable to life, although we can only speculate at this point, as we don't know enough about the planet's atmospheric composition or structure. The presence of an atmosphere would also be crucial for any potential signs of life, as it could protect organisms from harmful radiation and help regulate temperature fluctuations. It might also provide the necessary conditions for liquid water, which is essential for life as we know it. If the JWST can detect atmospheric features like greenhouse gases, such as carbon dioxide or methane, this could be another indicator that Proxima B might support life. Scientists are keenly interested in the potential for life beyond Earth, and Proxima B is one of the most promising candidates. While we cannot yet say for sure whether life exists on this distant exoplanet, the data we can gather from the James Webb Space Telescope will offer a clearer picture. The ability to detect city lights, or any artificial lighting, on distant worlds would be a groundbreaking discovery. It would not only suggest the presence of advanced civilizations, but also reshape our understanding of life's potential in the universe. In the coming years, as the JWST continues its observations, we may come closer to answering one of the most profound questions humanity has ever asked. Are we alone in the universe?